Welcome everybody. My name is Marcelo. I work for Facebook. I'm a software engineer, and I'm here today to talk about reflection using Facebook Thrift. So basically, let me just talk about the goals of this presentation today. I want to showcase a few examples of what can be done with reflection. Those are some real-world problems that we are solving at Facebook. This is should be useful for users, like to see what's possible, to follow some examples, and also for library writers to look at the problem from the perspective of Facebook. So the more use cases they have at hand, the better. And also, I'm here to present a working framework that can be used today. So it's not something that would have to wait for compiler support, for a new proposal to be accepted, and of course where Thrift applies, because you need Thrift in order for this to work. For those who are not familiar with Thrift, it's basically the RPC framework that we have of Facebook. So we write some definition using an interface definition language, basically saying those are the types that I have, and we generate some code for you based on that. And we won't look at how the reflection framework is implemented. I know some of you might be interested in that. But that's not the point of this talk. You can take a look at the source code later or come find me and I'll be happy to talk about it. But the focus here is to look at how to use it and what is possible. So, agenda here. So, just initial words first, and we're going to take a look at a few examples. Basically, code and how to use it. Then, how to enable reflection support in Thrift. A few closing words, and before I go, we can have some questions. So before we start, I assume you're familiar with reflection, the concept of reflection and introspection. High-level familiarity with serialization, just because one of our examples is basically serializer. Search algorithms like binary search or dictionary lookup. And of course, familiarity with metaprogramming. So if you're not familiar with metaprogramming, you never done some metaprogramming before, this talk will definitely not be useful for you. Things like metafunctions, specializations, trace classes, type lists. This is basically what a type list will look like in this slides. List transforms, basically how to apply a metafunction to every single element of a list. And we also have compile time strings, which is basically a type that will represent a string. This is not a runtime string that is allocated somewhere, it's just a type. Usually a variadic type, that's what we have in our implementation. So I'm gonna abbreviate a few things just to make the code more readable. So whenever you have a list of integrals, instead of writing integral const all the time, I'll just do it like this, just because it's easier to read. And also whenever you have a list of strings, I will write it like this, also to make the readability better. So let's start with the first example, a JSON ugly printer. I could write a pretty printer with proper indentation, but that's besides the point. You don't need to know reflection in order to write a proper indenter. So we'll take that out of the equation and focus only on the reflection usage. This is the interface that we're aiming for. Something really simple, just a function print where you pass an instance of your object, and we should figure things out and print it for you. Like, this is very useful for debugging, and given that it's JSON, you can actually use for other things as well. For simplicity, I'll just write to standard cout, but you could just send an output stream here or whatever you want and just write to it instead. So let's take a look at the implementation. What would this function look like? We start by reflecting the type class of this type. So basically what does that mean is it an integral, is it a floating point, enumeration, is it a struct, is it a list, a map, or what is it? The reason we need this is basically because we will implement the pretty printer in one way for lists and in a different way for structs. Lists don't have members that you have to iterate over, just elements that are homogeneous, whereas a structure may have several different members with different types. And an integral doesn't even have members, it's just a number. And the way we're going to do it is by delegating the implementation to some other template, very similar to what type traits do in C++. So basically say, give me the specialization of printer for this particular type class. So I want a printer for structs. I want a printer for integers, something like that. And then we just call the method print, passing the object that we want to print. So let's take a look at the general case for the printer. So ideally, we would just do this. Simply pass it to standard cout. It will just print whatever we want, and we're done. This works really well for integers, for doubles, but it doesn't work really well for lists or for maps or structures unless we have written an overload for the shift operator. But for integers, it works pretty well. So let's leave it at that for now. For booleans, we want a slightly different format. We want to write true and false instead of 1 and 0. We could use bool alpha, but we're just not going to do it because just for the sake of an example. So we just write an overload for bool, and there we have it. So the next thing is strings. How do we write strings? Ideally, we have to quote them because that's the format that JSON accepts. So we write specialization for strings. That's just a template specialization for printer. So whenever the type class is a string, this is what's going to be called. And we just write the print function, and what it does is writes the quotes, writes the value, writes the ending quote. Proper implementation of this would escape the string because we might have double quotes in the string itself. But for the sake of simplicity, we're just not going to do it and assume it's like there would be no invalid strings. You could simply write an escape function here and say escape what, and it would just work, but let's leave it at that. So let's look at lists now. Basically, this is the format of lists when it comes to JSON. You start with a square bracket, and you write every single element separated by a comma. It doesn't have to be strings. It can be any single object there. It could be structures. It could be other lists. But this is just an example. So what we're going to do is we're going to specialize the template for lists, for the list type class. And please note that the list itself receives the type class of the object it contains. So it may not make a lot of sense now, but it's very handy when it comes to printing the object that is contained in the list. We're going to make use of this shortly. Next step is to basically print the braces. And then we want to iterate over the list, just like we normally do. We're going to handle the delimiters. Just make sure we're going to delimit every single element with commas. That's nothing new. And right after, we call the proper specialization of printer for the type class of the contained element. So basically, we are on the list specialization, and whatever we have inside the list, we're going to delegate to that to properly print this object. So the next thing is sets. Like, how do we print sets? The format I chose is basically the same as lists. So let's see how we do that. It's pretty much the same thing. You specialize for sets. You have a type class of the contained element. And then you can simply delegate to the list. I mean, it's pretty much the same thing. So why re-implement that, right? It will make a difference later because the interface of a list and a set is not the same. A vector, for instance, has in place back. A set has in place. So we will specialize properly later, but for now, this should be fine. The next example is maps. So basically, this is the format of a map. You have curly braces. And then you have the keys separated from the values by a colon, and then the elements are separated by a comma. What we do now is we specialize for map, and just like we did for lists, we receive the type class of the key and the value contained in the map. The rest is pretty much the same. You write the curly braces, you write the for loop, you write the comma separators, you write the colon separators for key and value, and then you delegate to print of whatever the key and the value type is. Please note that by using the specialization here for printer, you can write the specialization for each type class independent of each other. You don't need to change the implementation of int to support a new type. You just add a new specialization and you're done. So the advantage of that is that you can even specialize in different headers. But it's just one reason. Like you can use any other implementation design you want to go with, but this is what we chose for this example. The next thing is how to print an enum. Like there are several solutions out there to like how do we figure out what's the string representation of an enum, right? So that's why most people just use the integer representation. We could do that, but I chose instead to use the string just to show you how we can do that, how you can convert an enum to the string representation itself. Pretty much the same thing. We have a specialization for enumeration, and then we want to see out with the quotes, and we call this function called enum to string. What this function does is just imagine a giant switch case from the enum itself to a string. There is a guarantee that this string will be statically allocated, so you don't have to manage lifetime of it. You can simply rely that it is stored somewhere and the lifetime is valid for the duration of the program. This is also useful due to the static initialization order fiasco. We had a lot of problems at Facebook with that, but you can rest assured that at least this part is safe. And the next thing is the structure. Like how do you infer what the members of a structure are, how to iterate over them, and how do you properly print? Because struct is basically, it's represented just like a map in JSON with the difference that it is heterogeneous. So the members don't have to necessarily have the same type. Basically the same thing. You will see that there's a recurring pattern here that's after a while, the part of the examples will become really boring because it's just the same thing. If you feel like it's boring, I've accomplished my goal, because that basically means you don't have a lot of cognitive load. You can simply say, well, I know how to solve this problem. Let's just go ahead and do it. Let's focus on what really matters, which is not figuring out how to iterate over types and whatnot. It is to solve other problems. So same thing, you write the braces, you reflect the struct. So that's basically saying, give me the information that you have for this particular struct. I want to know what's the actual structure that it has. Let's take a look at what that means. So basically, it gives you things like what's the name of a struct as a compile time string, what are the members of the struct, what are the annotations, because Thrift allows you to annotate types, members, and whatnot. And you could, the member descriptors look like this. It's almost the same thing. It tells you the name of the member, not the type, but the member itself. It gives you the type of the member. It gives you a getter function so that you don't have to say x.foo. You can simply say, give me this getter, and I'm just going to use it. I don't care what the name is. I don't care what the identifier is. I'm going to abstract that and write just generic code. And also annotations, just because Thrift allows you to do that. We're going to run through some examples later that use annotations to perform some data mapping, so that the goal is basically to say, I want to change only the IDL and not the code that I write in C++. And the reflection framework will just figure things out for you. And then now that we know what it gives us, we can simply say, well, I have to iterate over the members, but I have to know how to get the members first. So give me the information you have for members, and then I'm going to iterate over this type list. So the way you iterate over type lists is very similar to the way you iterate over types, over values, just not quite, because we're dealing with types here, not really values, right? But there is a helper function called for each, to which you just pass a visitor, and you say iterate over that, and call the visitor passing the type every time you find a new type. So for the first, and the index at which this type appears. So if you have a struct composed of an integer member, a Boolean member, a double member, and a float member, integer will be the first member of the structure. The Boolean will be the Boolean will be the second, double will be the third, and float will be the fourth. And as you can see, you can also pass additional arguments that will be forwarded to the visitor later. So you don't have to manage, you don't have to create stateful visitors. You can simply say, there's a visitor here, like give me whatever arguments I pass to for each. And with that in mind, we can simply say, well, iterate over that using for each. And whenever you find a member, call this visitor here and pass the member information to it. And also, of course, the structure itself. So let's take a look at how this visitor is implemented, because every time it's called, we want to figure out for this specific member, what is the type and how do I print it? It receives the member and the index like we saw before. This is just boilerplate, and it will also repeat for every single visitor you see. But it's simply you receive the type information first as a tag, either indexed or not, and whatever arguments you've passed to for each. And then you can simply say, if it's not the first element, print a comma. And also, I want to print the name. But the thing is that this name is a compile time string, but I need a runtime string in order to print it, right? You need it to be somewhere in memory. So what we do is we have this function called zdata. And what it does is whenever you have a compile time string, it will give you a null terminated, statically allocated string. So it's pretty handy. You just say, for this compile time string, give me something that I can use at runtime. And that's how you convert compile time to runtime strings. And then you call the getter on the member that you can get from the metadata that you received from the for each. And you can also get the type class for that member from this information, and you simply delegate to the correct printer implementation, and that's pretty much it. We're just iterating over the members of a structure and based on the correct type and type class, we're just calling the correct printer for it. And the last thing is, how do we print a variant? So I expect you guys are also familiar with variants, but basically it's a way to store at most one of different types in a specific container. So there's which is the name of what's stored there. So say I have a variant of foo and bar. Foo is int and bar is double. But at this specific time, I want to store foo in it, which is an int. So we're going to print the name of what's stored in there, the name of the member, and the value that's contained in the member. The way we reflect variants is through variant traits. Basically, we can say instantiate the variant trace for this specific variant, and I can give you the name of the variant and also the ID, which is basically the num that tells you which type is stored there. And you could say, for instance, print the name of this thing using zdata that we just saw. It also gives you descriptors for each of the members that can be stored in the variant. This is pretty similar to what the member descriptors are for structs, only that variants only store one thing at a time, and while structs have all the members at the same time. And the descriptor is a way for you to abstract access to the members themselves. So just like struct members, it gives you the type of the member, the ID of that specific member. So enum value x is going to represent the specific member. And also a getter so that you pass the variant to it and it returns a reference to that specific member. And a setter so you can actually set values in it. So this pretty much abstracts access to the variant so you can simply write generic code in order to use it. And an example of it is, say you have some instance of a variant and you've obtained the descriptor somehow to a specific member and you want to get the value of that member from the variant. That's what you do. And if we want to be sure, we can check if the value that's stored in the variant is the same represented by this descriptor. So let's take a look at how we implement the printer for the variant then with that information in mind. We write the braces, and from the type that's stored there, this is an enum value. This is a runtime value. We want to figure out what's the descriptor for this particular member that's stored in the enum. And this is a type. So we have to go from a runtime value to a type. But the problem is that at runtime you don't have type information, right? So how do you figure that out? And it's pretty much what we did before. It's basically with visitors, but we need a way to do that efficiently. So imagine you have some type with members foo and bar, and you have a list of those types with proper values, and you have a needle, which is a runtime value, and you want to get the element in this type list whose value of foo is the same as the needle. So you use the meta function getTypeFoo to basically filter the element by that specific member. There's a thing called sorted search, which is binary search. That's basically it. So we're going to binary search the type list, hoping to find a needle in there. You pass the needle, you pass a visitor. The visitor will receive the type itself as type information, and you can also pass additional arguments. Pretty much the same pattern we've seen so far, just for a different use case. So we just do that. We want to sort search based on the ID of what's stored in the variant. But the problem is, what if the list is not sorted? Like, you cannot really binary search in something that's not sorted, so you need something to sort the list. Let's take a look at how we do that. Imagine you have the same list, and again, we want to sort by foo. You just call the sort meta function, and it's gonna, you pass a compare because we want ascending order, and it's gonna return the list sorted for you. Pretty much the same, like very similar interface to what you have in the standard sort, just now for types. With that in mind, we sort the list by ID, and we pass this thing around to sort a search, and there you go. And you pass the visitor that you want to be called if there's a match, along with the variant itself. And let's now see what's the implementation for the visitor for a variant. So basically we have the member descriptor for whatever member is stored in the variant, and we don't really care about the index at this point. So we basically write the string representation of what's stored there, because it's basically the format we chose. We get a reference to what's stored in the variant, because we need to be able to print whatever is stored in there. And we delegate that to printer with the correct type class in mind. So whatever is stored there, we're going to forward it to the correct implementation. And that's pretty much it. That's how we implement a JSON pretty printer using static reflection. And no matter what types you come up with in Thrift, this will figure it out and will print it for you. So compare that to some of the approaches people usually do, which is like every time you write a new type, say a new container or a new structure, you have to somehow implement support for that in your pretty printer. With this at hand, you don't really need to, because Thrift will give that for free to you. So we pretty much don't have to change the code for the printer ever again. Don't quote me on that. So let's look at serialization now. How could we write a serializer? A serializer, it's sort of the same structure as a pretty printer, only now we have to deal with encoding, and we have to also support deserialization. So the way we're going to do that, I also want a pretty simple interface where you pass the object that you want to serialize or deserialize, and a data reader or data writer that's going to abstract transport or the buffer or whatever is the media that you decide to write this data to. So the data writer is going to be that. Like, I'm not going to go into the implementation for the data writer. We're just going to assume it works. But basically, you write raw will write the byte representation of the integer. So if you have to deal with endiness or encoding, this should be the place. And write string will write strings for you of the specific type. So as you can imagine, you would write the size of the string, and you would write the data, the underlying data of the string. That could be delegated to write raw. So I was talking to some guys about protobuf before this talk. We could extend this data writer to, say, emit protobuf, the protobuf layout format. Might need a few changes, but we can do it. And we also have a data reader so we can read the things we wrote with a data writer. This is not very interesting for reflection itself, but it's going to be what we're going to use for our serializer. So let's see how we implement a serializer. Pretty much the same thing as the JSON printer. We figure out the type class of whatever we have, and we forward it to the serializer, the proper serializer specialization, calling either serialize or deserialize, passing along the writer or reader. So the general case is pretty much like integers and doubles. What do? We write it raw, and we read it raw, and that's it. For strings, we write a string, read a string, no big deal. For enumeration, we write the string representation of the enum, just because we chose to. And you read the string representation of the enum, and you want to parse it. So this feature here, like enum traits, colon parse, it's basically a way to convert from a string to an enum value. It is pretty efficient. Internally, it builds a try at compile time, which is very efficient for string lookup. And whenever there's a match, it returns the value associated with each of the compile time strings. And there you go. You assign that enum value to the output of the serialize.
How do you get the error?
Oh, in this case, parse will just throw. We have other versions that don't throw. We will return you an error code. For this specific example, this is sufficient. So for lists, it's not that difficult. You write the size of the list, iterate on the list, and write every single element. Delegating is the proper serializer. And this serializer, you basically read the size, iterate that many times, create an element at the end of the list, deserialize to that element you just created, and that's pretty much it. This is not a very good API for lists other than stud vector. So if you use a stud string, for instance, it's not going to work because it's not the same API. We have something we call container traits in the reflection API that will abstract that for you as well. But just for readability purposes, I didn't use it here. I will upload more demos later to the code base so you can take a look if you're interested. But it's container traits is basically a way to say abstracted containers as well, so I don't have to know what's the underlying implementation. And you are able to register your own user-defined container and say, this is my container, this is the traits class for it, so the reflection subsystem can use that. And for sets, it's pretty much the same thing. Write the size, iterate, serialize, read the size, iterate, serialize into a local element, and then you place that into the set. For maps, also the same thing. Write the size, iterate, write the key, write a value. Read the size, iterate, deserialize the key into a local object, create the element in the map, moving the key in there, and just deserialize into it. So the next thing is structures. How do we serialize the structures? We know we have the information for the members, so we can simply say for each on that thing, passes a visitor that will serialize that for you. The members of a specific struct don't really change, so we can rely on that. For production ready code, you might actually change that. So we could decide to write a specific identifier for that member and say, and later we can say, whenever you're deserializing, check if this identifier matches something in the struct. We have this information available in the annotation. You can take a look at the serialization code that we have for Thrift if you are interested in that. But again, for the sake of simplicity and for time constraints, I haven't done that here. And let's take a look at the serializer visitor. Take the member. With the member information, you get the reference to the value. You serialize that value, and you need to figure out the type class as well. And there you go. So most of it is just figuring out the type class, getting a reference, and passing it around. That's pretty much it. Like I said, it should be boring. The serialize, same thing. You get the members, you write a for each loop, you pass around to a visitor, and that's it. Get the reference, deserialize into it, and figure out the correct specialization. For variant serialization, first we have the type itself. This is going to be pretty similar to what we did for the pretty printer. You have the type, you have to figure out the descriptor, do whatever we've done before, which is sort this thing, binary search into it, call a visitor. But the thing is, what if the variant is empty? Or yeah, that's pretty much the case. If the variant is empty, then sorted search will return either true if it finds a match, or false if it didn't find any match inside the type list of members. In this case, let's say we're going to write an empty string to say, hey, there's nothing written, there's nothing there. Assume this is going to be an empty variant. And this is the serializer visitor for the variant. We have the name here that we get from the member metadata, and we have to write that as a string. So zdata, the rescue. Zdata gives us the contents, but we also need the size of the string, right? So size is basically what, like you pass any compile time container, be a type list or a compile time string, it returns you integer constant with the size of that container. And there you go, you can write the contents of that string. And then you have to get a reference to the variant member, serialize, pass it around, there you go. The serialization, you read the string representing what's in there. Okay, so here's the thing. From the string, you have to figure out what's the enum member of what's stored in there. We could, for instance, parse this string into an enum and then use sorted search like we did before, but that would not be ideal. It would be much better if we could just perform the lookup from the string itself, right? So we want to look up in the names of the members of the variant. We don't want to have to convert that to an enum and then do it there. So how do we go from a compile time string to, from a runtime string to a compile time string? It is somewhat similar to what we did with sorted search, but instead of binary search, we're going to build another data structure. So say you have a list with a few compile time strings and a needle, which is a runtime string, and you want to look it up. So basically call try find, and what it does, like I mentioned before, it creates a try data structure based on those strings at compile time, and it basically looks the needle up. This should be pretty efficient. I have some benchmarks showing that is much faster than, say, looking up in a map or nested ifs or whatever, or even building a runtime try and looking it up. Pass it to the visitor will be called with a string if there's a match, and it will pass along any additional arguments you have. Same thing we said before. And we'll also return you a Boolean if they're telling you whether there was a match or not. And then with that in mind, we can call try find. So we pass the string to it, so we will perform the correct lookup, and we pass the visitor to it. And if it's not found, it means whatever was in the blob doesn't represent a valid member of this variant. So this will happen if we have an empty, if we serialize an empty variant, or it could also happen if we have an invalid value there, like whatever, but we don't really care about that right now in this example. And in this case, just clear the variant, like just make it empty. So the serializer, note that we don't receive the member descriptor here. We receive a name of the member. So we have to go from this name to the member itself. So it would be good if we could perform some lookup by name in the variant descriptor and say, give me whatever member information you have for this specific name here. That's what we do here. So we use reflect variant to get the information for the variant, and it provides us a by name helper that we can use for that purpose. And then you initialize that member inside the variant, like default constructed, just so we have the correct type setting there. We deserialize into that thing, but we need a reference to it, so we use get to get a reference to it. Pass it along. There you go. Now we have a deserialization for variant members. And there you have it. Like you have a full serializer in working condition. So the next and final example is about like untyped data translation. Say you have a map, string to string, like very common data. And this happens a lot in code, actually. And assume there's a structure to it. This is just like a fantasy example, but assume you have information like host name, host port, and whatnot. Since you have a map, and the map is homogeneous in the types it represents, you have to represent everything as a string. The thing is, for one, if I set something in the map, I'm not sure I'm using the correct key. Like, did I spell host port correctly? Or did I make a typo? Like, how do I catch this error? And also, is my number well formed? Like, am I passing some weird string there that doesn't really? So it would be nice if we could convert that to a typed representation of this thing. So say you're migrating some API from the old map of strings to string to some new API that takes a structure instead, like with actual type information. How do we perform this mapping? there should be a way for us to say, well, the member on the left is associated with the key on the right. So whenever you find this member here, that's the corresponding key in the map. We can use annotations for that in Thrift and say, in the IDL, this is the mapping. So whenever you have to update the mapping itself, either delete a member, update a member, add a member, you do everything in the IDL, and the code should figure that out for you. You don't have to change any code in order to do that. So this is pretty scalable because you change in a single place. You don't have to repeat yourself over and over, and for the reason it's not error prone. And if there's a problem with this mapping here, it doesn't represent a valid member or whatnot, it will tell you at compile time. And we want the public interface to also be simple. It should be as easy as translate. This is what I have, this is what I want. Right? So let's try to get that. What's the implementation for converting from an untyped data, say a map of string to string, to the typed version? Well, basically, you iterate on what you have, which is just a map, and you use the try find technique to say, well, let me know what's the corresponding member matching this particular key here. But the trick here is that it doesn't map directly to the member name. It maps to an annotation for that specific member. So we need a way to look that up based on the annotation, not on the member name. So this is how annotations work in static reflection. Like, you have the annotation name, which is property, and you have the annotation value, which is like host name, host port, client name, so on and so forth. So the thing on the right is the value associated to that annotation. We want the property annotation. This is the member of the name of the annotation we want. We want to get the value associated to that, right? We want to get that from the member information itself, because that's what the static reflection gives us. In order to do that, we write a meta function that says, given the member, return me the property associated with that member, right? It's going to look up this mapping that you just wrote here in the IDL and return you the correct thing. So we have to transform this list somehow to convert the members to the property values themselves so that we get the correct mapping. This gives us a type list of properties containing host name, host port, and all those things that we saw on the right here. And then we can try find on it based on the key that we got from the map. Call a visitor, pass the value that you have for that specific entry in the map, and the struct where you want to set it. And from there on, you receive the property here. Again, this property is not the member metadata, right? It's just a compile time string representing the value of the annotation. So we want to convert that property into the member descriptor. So we can do that by just performing a lookup in the type list. Fatal get here is basically the same as stud find. Given a list, I want to look an element in this list. And we basically say property is the member we want to look up, and the predicate is get property. So basically run get property on every element of the list and match that against property. This will give you the member metadata. You can use that to get the getter and pass the structure to it, and you have a reference to the element in the struct where you want to set the value into. Next thing is you need to convert the string that you got from the map, from the legacy map. You need to convert that string into whatever type you have in the structure, right? So Folly is an open source library created by Facebook as well. It provides you this handy converter here so that you can convert pretty much any like regular data type, say strings, integers, doubles. You can convert one to another. So from is actually string. Member type is whatever the member type is going to be. It's going to perform the conversion for you. And then you simply assign one to the other. And that's it. Sure.
So would boost lexical cache work there?
Sure. Yeah, it's just values. Like you're looking into a map of string to string, and the question is, would boost lexical cache work? So they pretty much serve the same purpose. You're just getting a string and converting to an integer, double, or whatever. So translate. We want to convert back from the flat config, which is a structure, to the legacy config. How do we do that? That's actually much simpler because now you have the member information itself. You want to get the members, you know which members you want to get from. Basically everything that's in the struct, right? So you don't need to look something up. You just iterate over the members of the struct. So you pass this member information to for each, call a visitor. Again, the same boring thing. In the visitor, you receive the member information, use that to get a reference to it, to the member of the struct. And you wanna also get the property name associated with that member and use that as the key. But first you have to convert that to a string, right? So we do that. Now we have the value and the key itself. Next thing we do is convert the value to a string because we have a typed value from the struct, right? It could be an integer. Convert that to a string and set it in the map to the appropriate key. That's it. And we're pretty much done. So with this code, it's actually 2 visitors and 2 entry point functions. We can convert back and forth from a flat config from an untyped config to a flat structure. What if we wanted to convert it to not to a flat structure, but instead to a nested structure, saying like, I want the config to contain another struct called address, which by itself contains host and port, so on and so forth. Like it could be deeply nested because it's much easier to organize information this way. We could simply recurse like we did for the pretty printer, for the serializer, and perform the correct conversions. I had another example that that makes it much simpler by flattening all the getters of a specific structure, nested structure. So you get a single list with every single leaf in the structure. But I had to cut it off of the presentation for time constraints. The demo will be uploaded though to the Thrift code base. So very, very shortly you have access to it. I'm gonna provide the slides with that example as well in the repo. So how do we enable this? Like, because so far it seems magic. Like there's a lot we can do, manipulate those types, introspect into the structure of the program. But how do I get this? Like, do I have to write a bunch of macros and manually fill in the blanks? Actually, no. Say you have the module.thrift, which is basically the IDL containing all the types that you care about. And say you want to call Thrift, just like you usually do, to generate C++ stubs, RPC information, and whatnot. The only thing you have to do is add a flag called fatal. It's not a very good name, but because it would be much better if we had reflection in there, say generate reflection information. This for historical purposes. I'm changing that, and I'll land soon. I hope to land a change soon to change that to reflection. But for now, that's how we do it. But watch out for this change. It will be reflection in the future. And then it's gonna inside a directory where Thrift usually puts all the files it generates. There will be a few other files there as well. That you can then include to have this type information. And that's all you have to do. You just include the correct module and you use the flag in the Thrift compiler. How do we import this metadata? You just include a file. So for structure information, for structs, it's in a separate file. Enums is yet another file. Unions is basically variants. It's just the way Thrift names those things. It's in yet another file. The reason we separate that is because maybe you're not interested in all this metadata, just in a few of them, and you don't want to pay the price for the build time price for including all of it. But if you do, there's a handy header called underscore types that you can include to have all of this. There's more information in the source code. There's a header. The main header for reflection is called reflection.h. By the way, the path is also going to change from fatal to reflection. But reflection.h contains like a lot of documentation in line that you can simply take a look at. It explains to you how to generate this metadata, how to include this metadata, how to troubleshoot in case there are problems. Information is all there. And so a few closing words. Some places where we want to use this, we've been experimenting with. I had an intern recently, thanks Dylan, who re-implemented all the serialization framework that we have. to instead of generate the serialization code in the Thrift compiler, to use static reflection instead to generate that for you, right? So impressively enough, we've seen gains in build times because of that. We're still not sure exactly why, but so far we think it's because parsing and token validation and all that stuff, it's very costly. So instead of including the code everywhere, you're just instantiating the templates where you need. So for a specific file that's compiled by Thrift, it might not make a difference, but for big projects, it makes a lot of difference. Like I don't have numbers because I finished the slides like 30 minutes ago, but we're still experimenting with that. There are still some improvement we can get. Well, let's see. Let's hope for the best. There's also runtime performance, just because we think it's because the compilers do a good job at optimizing templates. I'm sure there are a lot more we can do, but things like building the try at compile time or building a sorted list at compile time, it's work that you don't have to do at runtime, right? And also some other things, like there are a lot of transformations that we're doing in the types themselves that are done at compile time and we don't have to pay the price for them at runtime. So that may also be a contributor to that. And symbol size reduction, just because we have full control over the implementation of serialization, we will also have that with regards to the Thrift compiler, right? But the thing is, if you're writing serialization for a specific structure, you have to either put that in the structure itself and say read, write, whatever, or you could write a separate specialization, but the name of the structure has to be there, the name of the members has to be there, so you don't have a lot of control over the naming of things. With this, there are lots and lots of templates that we can actually just change the names and shorten them so that the symbols themselves can reduce in size. And also because a lot of the transforms are done at compile time, every time you see a using statement, that's computation that's not being generated as runtime. So it's a function that's not being emitted. So that's less code to compile and less symbols to include in your binary. Native cross-language extensions. We just talked to some guys that work with Python and Facebook. We don't have any progress yet in this, but we're interested in, for instance, using this to generate the Python bindings instead of generating Python code. So it's a lot less code that you have to generate in Python, a lot less code that the interpreter has to parse. And basically you can have the reflection subsystem take care of generating everything for you. All you need is a call to one function that will generate all the types you need and register it in the Python interpreter. And I think the biggest gain from this is cheaper experimentation. Should you have a need for a different serializer, or you need a comparer for this specific struct here, or you need, say, a specific transform like merge or whatnot, or pretty printer, you don't have to change the Thrift compiler in order to implement that. You can write that as a separate library that's not intrusive because it doesn't change any other code. It's just a separate file there that you don't have to include if you don't want. So it's much cheaper for you to experiment with. You need to be able to write metaprogramming, but it's still much cheaper than understanding how the Thrift compiler works and changing that. And believe me, it's pretty messy. And runtime reflection. All of this that I presented is basically compile time reflection, right? But the metadata is all there. And we've seen that there are ways to convert this compile time metadata into runtime information. So I'm planning to investigate a little bit on how to convert that to runtime right now. There are some benefits to it. For instance, build times. You don't have to instantiate a lot of templates. You can simply use like iterate over data. You pay the price for runtime performance, but in some occasions you just don't care, right? And also, although runtime reflection is a little bit limited because you don't have access to the types themselves, there's a lot more people that can use the runtime reflection than there is people that can use compile time reflection. So you wouldn't need metaprogramming skills, for instance, to use runtime reflection. So it's something that I'm also planning on adding soon. C++ standard support. This is not at all a take into suggesting something to be included in the standard. Basically, I'm sorry. Basically because this is not generic enough to be used by C++. It only fits Thrift use cases, which for us does the job most of the time. But I think the best thing that this can provide to whoever is writing a proposal for the standard for static reflection is basically this. Those are the use cases we've seen so far where reflection can be applied. Those are ways that we modeled compiled reflection for these problems. Some of them are good, some of them are not so much. So it's a way for you to see, it's a different perspective where you can see what can be improved here, what is the good things that we can reuse, and whatnot. And what use cases should it be focused on, and that my proposal should actually address. And the last question is, why not write then a compiler patch? C++, like say for a Clang or GCC? Well, several reasons. One is this is not generic enough and will take a lot more, it would be a lot more costly to implement something that's C++ worthy, as opposed to something that suffices the subset of Thrift that we care about. There's also another reason. In Thrift, there's a single implementation of this. If we were to change the compiler, we would have to support at least Clang and GCC and probably Visual Studio. I don't have access to the sources of Visual Studio. And whatever other compilers that people decide to use. By having this in Thrift, this is pretty much C++ 11, so any compliant compiler can use this. By doing that in Thrift, it's just cheaper for us to do it. The only downside is that now you have to include the field files to have access to this, but you might be fine with it. Hopefully, I will delete most of this code whenever reflection gets in the language. I very much want to do it, but I think for a while now I won't be able to, so let's use what we have, let's experiment with it while we can, so that when we get something, we have a much better idea of what we want and how we can accomplish that. And before I go, I just would like to use the remaining time for any questions that you guys may have. Thank you.
What's the rationale for this being a static template library as opposed to just using the runtime description?
Like I said before, yeah. Sorry. The question is, what is the reason for having static reflection as opposed to runtime reflection? If I got it correctly. Well, for one, I can generate runtime reflection from static reflection. I cannot do the opposite. Like I said, runtime reflection is support that I want to add, and I can use very similar techniques to get that. The other thing is that runtime reflection is pretty limited because I don't have access to the types. Like I said before, I would not be able, how would you iterate over a structure using runtime reflection? There's a lot of indirection type erasure that you have to get in place. And that has a cost at runtime, right? And also, runtime is also another reason. Like we work in a very large scale at Facebook, and we care a lot about performance. By having a lot of the computation happen at compile time, sometimes it bothers developers, and I completely understand that because you have to wait longer for it to compile. On the other hand, it's like when you put that to thousands of servers out there. There's a lot of benefit that you can get out of it, right? Is less time that you're processing all those services, all the servers. So yeah, that's pretty much it. All right, so there are no more questions. Thanks for watching.